In this problem, we're told that we have a river. Here's our river here, and there's a current flowing in the river. It's flowing southwards at 2 meters a second. The river is 800 meters across, and we have a little motorboat here, and we start off on the west bank, and our goal is to get to the east bank. We're told that our motorboat is capable of traveling at 4 meters per second relative to the water. Okay, so we want to figure out what's going to happen in this scenario. So we're going to point our boat so that it's aimed directly across the river. But because of this current, we're not actually going to move directly across the river because the current is going to cause us to drift southward. So the actual motion of the boat, if we just point it this way, it's actually going to end up moving something like this because of the current. And that's what we want to analyze. Okay, so to start off, it's probably a little bit easier to first consider the case where there's no current at all. Now, if there's no current, so the water is perfectly stationary, then we're told that our boat here can travel at a speed of 4 meters per second relative to the water, and we aim our boat so it's pointing directly east. And so what's going to happen? The boat is simply going to move directly across the river because in this scenario there's no current. And if I say how long is it going to take the boat to get across the river? Well, it has to travel a distance of 800 meters, and it's traveling at 4 meters a second. So we can use rate times time equals distance. And so in this case, we're traveling at 4 meters per second to the east for some unknown amount of time, and we want to cover 800 meters. So we see that the time is going to be 200 seconds. Okay, that's the case if there is no current. But in our problem, we do have a current. So as we attempt to travel straight across, the current is going to cause us to drift downwards. And so the net effect is we're going to move sort of along a diagonal line like that. Okay, so how do we analyze that situation? So here's the basic idea. Okay, here's our boat again. And the boat is capable of traveling at 4 meters per second relative to the water. But the current is flowing southwards at 2 meters per second. So to find our velocity relative to the ground, we're going to add these two vectors. We're going to add the motion of the boat relative to the water plus the motion of the water relative to the ground. And when we add those two vectors, that's going to tell us how the boat itself is moving. So we add these two vectors. Remember, we add vectors. We place them head to tail, and then we draw an arrow like this. And so that red arrow represents the velocity of the boat relative to the ground. We can get the size of it by using the Pythagorean theorem. The size of the velocity of the boat relative to the ground is given by the square root of 4 meters per second squared plus 2 meters per second squared, which is equal to the square root of 20 meters per second. So that's how fast the boat is moving relative to the ground, and the direction that it's moving is in this direction right here. Okay, now we're asked a few other questions about this. We're asked, for example, how long will it take the boat? So as the boat travels across, it's going to be traveling like this. How long will it take for it to reach this eastern bank? Okay. Well, again, this is its actual motion here, but we can think of it as being composed of two pieces, a rightward motion of 4 meters per second, plus a southward motion due to the current of 2 meters per second. Well, this southward motion doesn't actually help get us across to the other side of the river. It's only this portion that's actually helping us cross the river. So, if we want to figure out how long it takes us to cross, we can again use rate times time equals distance. In this case, we're going to say the rate at which we're going horizontally across is 4 meters per second times the time is, we want that to equal the distance across, which is 800 meters. So again, we find that the time that it takes for us to go across is 200 seconds. Notice that's exactly the same result as when there was no current. Again, the way you should think about this is that the motor on the boat is trying to send the boat this way. Meanwhile, as it's moving this way, the current's causing it to drift southwards. But that downward drift doesn't affect this piece of the motion here. So it's still moving across horizontally at 4 meters per second, just as if the current wasn't there. Okay. We might also want to know, okay, so if the boat in fact travels like this, when it lands on the other side, it's going to end up here. In other words, it's going to end up south of where it started. So it starts here, and it didn't go straight across, but it ended up south of where it started. And if we want to know how far south the boat ends up, okay, so again, the boat starts here. It was aiming this way, but it didn't actually go that way. Because of the current, it ended up going like this. And we're interested in knowing what is this distance. So to figure that out, we can do the following. We can say, well, we know that it takes 200 seconds for the boat to traverse the river. But during this 200 seconds travel time, it's traveling southward at 2 meters a second. So we have, it's traveling at 2 meters per second for a time of 200 seconds. So the distance that it covers, so it's traveling south at 2 meters a second for 200 seconds. So rate times time is going to equal the distance, and in this case it's 400 meters. So that's how far it's going to travel southward as it's going across the river.